differentiation rules, or differentiation rules, depending on how we're looking at it. Differentiation is really an awesome, awesome thing. Today we are going to look at and investigate the different rules for differentiating different functions. I don't know about you, but the first principles, I think it takes a little while. And mathematics is all about patterns. There's got to be a better way. And ladies and gentlemen, there is, and we're going to look at many of those right now. So we're going to start with simplest function there is, a constant. F of x equals 7. Well, what's the derivative there? Remember what derivative is. It's the gradient of that curve. And a lot of times it's an equation. F of x equals 7, in other words, y equals 7. Think about what that looks like. It's a horizontal line, and any constant is going to be a horizontal line. What is the slope of that line? In other words, what is the derivative of that line everywhere? Well, it's 0. The gradient, the derivative of any horizontal line of any constant function will be 0. Neat. Let's take a step up. Derivative of a power. Okay, so we're going to derive this. We're going to derive many of the rules for differentiation using our first principles. So finding our derivative, f prime of x, is going to be the limit as h goes to 0, x plus h to the n minus x to the n, f of x plus h minus f of x all over h. Okay, well, where do we go from here? There's a property in mathematics that says a to the n minus b to the n is equal to a minus b times a to the n minus 1 plus a to the n minus 2b plus a to the n minus 3b squared plus da 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 da. It's a lot like the binomial expansion. We've used this factorization every time we factor difference of squares, but this factorization is more general than that. It works for all difference of powers that have the same exponent. And we can use that in the numerator. This is a difference of two things raised to the same exponent, so I can factor out x plus h minus x times x plus h to the n minus 1 plus x plus h n minus 2 times x plus da 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 plus x plus h x to the n minus 2 plus x to the n minus 1. And this is all over h. Well, look at what happens in this first factor. The x's go away. Limit h goes to 0 of h times stuff over h. And, well, will you look at that? That's nice. The h's are going to divide out, and we're left with the limit as h goes to 0 of x plus h to the n minus 1 plus x plus h to the n minus 2 times x plus da 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 x plus h x n minus 2 plus x n minus 1. And this is something we can take the limit as h goes to 0 of. We've gotten rid of that dividing by h thing that causes problems. So as h goes to 0, we have x to the n minus 1 plus x to the n minus 2 times x plus x times x to the n minus 2 plus x to the n minus 1. And all of these terms are x to the n minus 1. But the question becomes, how many? Well, it turns out if we look at that expansion, we will have n terms. So we have n times x to the n minus 1. So what does that mean? Well, let's summarize this. Let's wrap this up into a nice package. If f of x equals x to the n, then f prime of x, the derivative of f, is equal to n times x to the n minus 1. Let me describe this to you in simpleness. We take the exponent and we bring it down in front. And then we decrease the exponent by 1. For instance, if f of x was x to the 6th, f prime of x, the derivative of f, would be 6, bring the exponent down, x, and then we decrease by 1, so 6x to the 5th. Neat. Cool. No longer need to use our first principles. Now, what about multiplying by a constant? Because, well, we don't always just have x to some power. Sometimes it's 2x squared. If we have f of x equals c times g of x, the derivative of f will just be c times the derivative of g. So if we had, I don't know, 1/3 x to the 6th as our f of x, f prime of x says, leave that constant alone, don't do a thing with it, and then differentiate the function that we're multiplying it by. So differentiate x to the 6th, well, we saw that we bring the exponent down and multiply by x to 1 less, and this simplifies to 2x to the 5th. Next rule for differentiation is when we have a sum and difference of functions. Because we've seen polynomials. That's a sum of a bunch of little powers. So how do we deal with this? Well, let's derive it. Let's use our first principles. It's going to be wicked fun. And we're going to do it for the sum of 2. To derive plus or minus sum and difference, we'd have to do this twice, but the same thing is going to hold. Limit h goes to 0 of, now we're going to do f of x plus h, so that's going to be ux plus h plus vx plus h. That's our f of x plus h, that whole thing. And then we're going to subtract f of x. And of course, that's all over our good friend h. Well, we can do a bit of rearranging here. Limit h goes to 0 of ux plus h minus u of x plus vx plus h minus v of x. And well, those are both over h, so let's just do that. Split it into two fractions, one with the u's, one with the v's, and we have properties of limits that says we can do this. And ladies and gentlemen, I hope you're jumping up and down, screaming in your seats, saying, wait a minute, that's just the derivative of u plus the derivative of v. So what this tells us is that if we have the sum or difference of several mini-functions, we can differentiate each term separately and then add or subtract them at the end. And now let's do a couple of examples. We want to differentiate y equals this big polynomial with respect to x, and that with respect to x thing becomes much more important later on down the road. The rules that we're looking at right now are differentiation with respect to x. So, we could do this with first principles. If you want to, quite frankly, you're a fool. Let's use our power rule and combine these last few things together. So y prime, or we could say dy dx, derivative of y with respect to x, is equal to 1/4 times 5x to the 4th minus 3x squared plus 5 times 2x to the 1st minus, well, this is 1, it comes down, 1/2 times 1 times x to the 0, and derivative of a constant is 0. And let's clean it up. 5/4 x to the 4th minus 3x squared plus 10x minus 1/2, because of course x to the 0 is 1, and here is my derivative. Second example. Find f prime of x if f of x is this quotient where x does not equal 0. Well, but wait a second. We haven't talked about anything like this. Well, actually we have, guys, because we can rewrite this. We can notice that, okay, f of x is 2x squared minus 3x plus x to the negative 2nd. I'm dividing each term in the numerator by x squared. And now I have this polynomial written as 3 little power terms that I can differentiate using my power rule. So f prime of x is, pause, you try. So hopefully, the first term, you have 4x minus 3, and then minus 2x to the negative 3rd. Remember, we decrease the exponent by 1, and we bring that original exponent down in front, and I'm fine if you leave the answer this way, or know that it's equivalent to that. And that's where we stop for this. As we go into the next couple videos, we're going to look at some functions that get even more and more fun, and these derivatives are going to rule even more.